Yeah, my name is Charles Bhaskaran. I'm going to talk about noise, vibration, harshness analysis, talk a little bit about simulation, testing, and validation of marine systems. So we're talking about boats, those kind of things, and how noise, vibration, harshness happens, and how can we use these kind of techniques to design products. So basically, that's the whole idea. Here, that's the central area of importance to customers nowadays that they all want less vibration, and it has to be highly durable and very low noise so that people can be more satisfied. A lot of these boards are very expensive pieces of equipment, and these become important in today's world. Noise can come from a lot of things, right? So I took a special area where everyone can relate to, and the world is going after electric today. So the noise issues in electric propulsion. So what we see in the picture on the right is basically a random profile and their responses to cavitation conditions in a propulsion system, right? So there is a propeller uh, in the boat, and when the propeller goes into cavitation, what do we see? So you can see the red is basically a wetted propeller with no cavitation conditions, and the blue is something where the cavitation actually happens, right? So on the right-hand side a picture, you will start seeing this two the same. Some of these are kind of excited differently. So every time the blade passes, there is a blade passing frequency, right, that attaches to the noise. So all we are saying here is the blade passing frequency is the most dominant sine tone, and there is a background noise which happens in electric propulsion as well. So in general, in propeller noise, we talk about imbalances, tip and hub vortexes, and things like that. Electromagnetic noise, we talk about magnetic field in the air gap, right? So there are a lot of radial and tangential forces. Eccentricities and things like that can make the noise worse. And then we have the controls noise. So when your control is smooth, TID smoother, and you don't hear that kind of variation in speed or any torque fluctuations. If your motor has a lot of uh, torque variations or speed variations, the noise will be propagated, right? So that is why it's really important to have a smooth transition rather than a step transition. There's another piece where the noise can become really dominant is the resonance or mechanical frequencies, right? So the motor itself, the housing can vibrate, the shaft can vibrate, the bearings, when they all do the vibration, it is heard as noise. And one thing, main thing that is all that is happening here is the hull and deck vibrating in a boat. It again vibrates the rest of the structure. So all of them are noises. So how do we design a quiet thing? So we have to design the motor appropriately, like we talked about, electromagnetic noises and things like that. Propeller, a lot of the vortexes, we have to be careful about those. Whirling of shafts, high-speed bearing issues, transmission noise, gears have a lot of rattling and things like that. We have to reduce the whining, rattling, housing vibrations, column bending, creates a lot of problems. Mounts, decent design of mounts. A lot of the vibration today is isolated with isolators. Basically, we have to reduce all the harmonics, seal them so that you can continue. Uh, there are some of the metrics we look at: loudness, sharpness, roughness, fluctuation, strengths. All of those are, very specific to how we have bring sound quality. And here I talk a little bit about the propeller noise a little bit higher. So there's a lot to cover, so I keep going. And what you see on the right, we kept talking about the step vortex. And you can kind of see on the right-hand side, when a cavitating propeller, you can kind of see that glass little thing like a screw. That is basically because of the tip of the propeller. And at the root of the propeller, there is also some issues going on. You could see there's turbulence happening in there, and that the hub of the propeller also creates the wake. So the tonal components we talked a little bit about, are coming from the tip, and then the hub and mainly the broadband is coming in from the hub, vibration happening or whirling happening in the hubs. There is a phase change that happens. So it's two different densities in the water. So when air comes in, that makes a lot more noise, right? So it's very critical to make sure that the propeller does not cavitate. And the tips are designed so that they do not have a lot of vibration. Other issues, if you don't mount the propeller correctly, damaged propeller, loose fitted thingies, those all can act as issues. Propeller wake is a big acoustic source, and its wide frequency range. And then the cavitating, we talked a little bit about the higher tonal noises. Anything which is about more than 10 decibels difference, and the second harmonics and the third harmonics and the fourth harmonics, each one have their preferences, and whichever one is exciting will be louder. And we talk a little bit about the electromagnetic noise. The picture, what you're seeing on the vertical lines that you see, those are the natural frequencies, right? So on the x-axis, we have frequency. On the y-axis, we have RPMs. So anything which grows diagonally, you could kind of see there's a lot of PWM excitations happening. This is the motor pulse width modulation. You can kind of see those creating noises. And then the slotting noises that are coming in from the motor, the slotting excitations, those are all really critical. And as we talked a little bit about the magnetic field and the radial and tangential noises and the forces, they create noise, right? So we have to be designing to excessively less radial and tangential forces. And the smooth motor, typically, we can kind of see that the rotor stator eccentricity is one of the main areas. The imbalances, the natural frequencies, keep them low. Typically, the lower switching frequencies it induces a lot of harmonics, so it's very noisy. There's also differences between triangle versus PWM modulation, where the noise kind of changes. Single versus the winding of the motor itself. You double wind the motor, it's quieter. And there's a lot of harmonic content, magnetic forces that happen. We don't want it to be concentrated. It's better to be distributed. High cogging torque, so we design the motor so that these high fluctuations in noise can be reduced. Lower number of slots, holes, skinny air gaps, magnet shapes. You could play with a lot of these things to reduce the motor noise. Talked a little bit about the controls, and the whole idea is to keep the output reduction. You could do skewing, notching, slot opening, those kind of things. Now we talked a lot about noise. We get into the vibration portion, and vibration in marine is fairly severe. And this is an example. I'll try to play the video. If it comes on, it's okay. Otherwise, it's hard to play. It's not playing correctly. So I'll talk through it. So these kind of waves are happening in a channel in the U.S. And this is one of our boats. So you can actually see how violent the boat is jumping all across in the water. So all of those are severe vibration and shock happening in the boats, and that will be transmitted to the humans in the vehicle. So that is why it's very critical for us to design so that these shocks can be managed. So boat vibration causes shock, fatigue, user discomfort, kind of things. In the motion of the sleeve slamming, you actually saw the hull is vibrating. Machinery in the products, in the boat is vibrating. So engine, gearbox, propellers, generators, all of these are vibrating. Just to split differently, the torsional vibration comes from the engines, propellers, shafts, etc. On the longitudinal vibration, when the boat's going forward, we get a periodic alternating thrust, which is basically the engine produces the thrust, right? So that thrust creates vibration. The hull curvature of the design of the boat, and how the water flows through the boat creates what we call the wake. So how fast you go, what kind of wake the propeller blade does gives you that vibration. How the water flows through the prop, top versus bottom, and at different degrees as it's rotating, all of those are really important. So if there's something weird, then it'll start vibrating differently. And those prop excitations are accelerated by the number of blades, right? So every time the blade passes that area, it's creating that vibration. Lateral vibration is, if you can imagine, left to right kind of thing. So those critical speed frequencies. Those happen in the engine shaft, bending, whirling, all of those are translated into lateral vibration. So in general, they're very less, controllable. You cannot control the water, you cannot control the wind. You can only control it with stiffness, mass, damping, and make sure that the propeller and other rotating components do not have high vibration. So we talk a little bit about the complexities in terms of vibration. Right? So there is random components happening because we have different speeds, there's various different sea conditions, right? The waves are changing, wind is changing, the boat maneuverability is changing. And then there's these periodic contents that comes in. So random is it all happens at the same time. There's no repeatability to it. And then there's this periodic content which comes when the hull is resonating. So if the hull is resonating at its resonance, that's a periodic content. When the propeller rotation always rotates, that's a periodic content. So we are getting both of these happening at the same time. So in the picture, what we are showing is there is a lot of different frequencies are excited in different times. So there's truly a random thing that happens in reality. Once in a while, you get the sign basically from the engine or any reciprocating component. So anything that is mounted on the hull, which gets this high transmissibility, and typically we see like masts and things like that where we mount sensors, antennas, they have very, very high transmissibility for that reason. So the mounting structure, what I'm saying is really important where you mount it and how that product is designed for vibration. The bow of the boat is the front of the boat, and the side of the hull, how smooth they are will reduce the turbulence, right? So the turbulence noise is really critical in how you make the boat, how you smoothen the boat. You don't want any squared off things where it creates a lot of turbulence. Then we see a lot of vibration on the backside of it. So just to give you an idea, there are deep V boat hulls and flat bottom fishing boat hulls. The deep V is basically cuts through the water. It has a lot of friction. The noise and ride is very nice. But the flat bottom boats, fishing boats, they have to go faster. So half the time, they're just bumping on, bouncing on the water. So those boats vibrate a lot. So best is to collect some data so we understand, what kind of vibration is the boat actually seeing. And to the right, this is just a picture of what we call a waterfall, just showing you the signature of what kind of energy content, frequency content we have in those in real life data. We get into simulation a little bit. We talked a little bit about noise. We talked a little bit about vibration. Now we can talk a little bit about the simulation component in the design. So when we design vehicles, just like in any other industries, we can do certain kinds of analysis to find issues, right? So every product has their own modes. And in the right, at the top, right-hand side, you can kind of see the mode one is how the boat bends. This is the primary mode. Mode two is lateral bending mode. And then you can see mode three, the second wave happening. It's basically the higher version of mode one. The mode four, you could kind of see how it's twisting. Mode five is basically another wave happening. So imagine on the mode five, you have a product which is sitting on top of that hull. It's going to see a lot more vibration when that natural frequency of the vehicle is excited. Mode six is on the higher order mode of mode two. So this is just an idea of, we can do these kind of analyses. We call it linear dynamics, modal analysis. And the modal analysis can actually show us the natural frequencies. We know that the random vibration is very dominant, wind and wave fatigue, right? So we can simulate random vibration in the analysis. We can simulate sinusoidal engine propeller resonances. All of these we can model and simulate it today. There is a piece of analysis which we call explicit dynamic solution. So when we actually physically hit something, example would be, yeah, a boat is actually hitting the waters, would be an explicit dynamic simulation, or it's going and crashing into something. So those are nonlinear responses, which we can also do. There's analysis we can do for shock loading, and there's analysis we can do today with multi-axial fatigue simulation. So there's fatigue models out there that we can use for multi-axial fatigue. And there's various acoustic simulations you can do today in addition to hybrid methods and high frequency methods. Just to get a little bit of more into multi-physics simulation is available today. We use it for wave hop, right? So what you're seeing on the right-hand side picture is a boat bouncing in the waves, and you can see the pressure in the hull, right? You can see things like that. Underneath the blue that you're seeing, that is basically the stresses developed under the hull. So we could do a lot of those kind of wave hop simulations, aero hydrodynamics, flat wave versus 6-foot waves, fluid structure interaction analysis. That's basically what you're seeing in the picture. And propeller CFD, I think we showed a little bit of the CHA. This is detached eddy simulation. RANS is basically, Reynolds large eddy simulation, two-phase flows. These are all very common today in the CFD world. So we look at lift drags, unsteady flows, volume of fluid, turbulences, multi-body dynamics for 6 degrees of freedom, NVH optimization, and there's also for forces, we could do model-based systems engineering. Got a little bit time left, so I talk a little bit about testing and validation. So we can do lab, which is a control testing. We could do on-water boat testing, and then on-road trailer testing. A lot of these boats are actually trailered, right? So there is a lot of rough water conditions, as
Yes,
turns. Yeah.
Dr. Charles, you have more time. Please take more time, no problem.
Okay. So there's these kind of different kind of testing condition. Rough water means like it's seriously rough. You don't even want to go into the sea, right? So we collect that kind of data. And there are different turns, crosses, cruising, accelerating to plane, oversteering, going fully fast and then turning. All of these are really like wind wave condition. You're going into the wind versus going away from the wind. They all make a difference. So we have to collect a lot of these kind of data and then go and do some testing. When we say harshness testing, there's a lot of techniques today that we can actually simulate real world conditions. Basically, you go in and collect a bunch of data, and then we come in and create these kind of testing mechanisms. What you see in the blue color is an electrodynamic shaker. The electrodynamic shaker is very commonly used today to create a lot of these kind of conditions of vibration and shock. This also can be multiple. You can do it one axis at a time, and there's also multiple shakers now utilized to run all three axes. So there's these are called on the right yellow. What you're seeing is basically what we call a hexapod or a mast. It's a multi-axis a hydraulic servo hydraulic system where it creates that 6 degrees of motion. So you can kind of do things like that to simulate real world. And we want the different conditions also stimulated, right? So the thermal cycling, hot and cold, in addition to humidity and in addition to um, vibration, would create that real world environment. And in today's world, all our vehicles are IoT sensor integrated. They are doing predictive analytics, machine learning, those kind of things to understand what kind of information is that we are gathering. Accurate real-time simulations, or you could go read up on HALT, has ADT, ART. These are like accelerated tests. So if we are trying to simulate a 20-year life, we go in and collect data, and then we highly accelerate that test for maybe in a week. So a whole 20 years can be simulated in a week. So acceleration factors become important. And some of the areas, when it gets into the army, there's reliability growth handbooks and things like that you can look at. Fundamentally, the HALT is designed to understand weak links. Okay, so that those are like the normal stressors, and they do a very good job of gradual wear out failure modes and normal stress variant modes. But then we get into the HAS type of models where those are identified mainly for production process issues. So, those kind of things. You probably heard about the bathtub curves. Those are things that are happening. So it's very traditional to do statistical design of experiments, Weibull type of analysis to make sure that you have plenty of life left in the products. This is my last slide, talk about validation. So validation is gets a little bit more in depth into the vibration and the shock and the BSR components of it. So what you're seeing in the right hand side is an engine driving down a car driving down the path on the right lower the right hand side lower picture where it shows you a track is basically where a run up is happening. And the red curve is showing you the X, and the green is showing you the Y, and the blue is showing you the Z. And the spectrum is actually shown in where the run-ups, you could see all the frequencies that are actually, we call it orders. So those different orders are can be understood based on the product. How can we use this data to simulate real world conditions? So we talk about when we collect data, we start looking at the peak accelerations, the velocities, the displacements. In most cases, what we will see is non-Gaussian happening. There's no repeatable patterns in them. They're all random in nature. There are many things that we look at called kurtosis, crest factor. Basically, what crest factor is the peak acceleration to the RMS. So we have to excite all these resonant frequencies and be more realistic, right? That is why we look at all of these um, peak accelerations and intensity. How intense is the shock? Those kind of things. And we talk a little bit about field data replication. Why do we do field data replication? So we basically get data from the field, and then we play it on our electrodynamic shakers or servo hydraulic machines or hexapods. And the real interesting thing we do here is the real intensity. It's one-on-one. We don't accelerate anything. We just get the real intensity, what is going on in the real world. You could basically try to do a multi-control in different locations of your product, and then you can simulate the exact nature and control the shaker the same way what's happening in real time. That is why the field data replication is used in the industry, real intensity, right? And then we have what we call FDS. FDS stands for fatigue damage spectrum. And this is a method used for Gaussian spectrums. Basically, we get a whole bunch of time histories. You just go do your tests, do the S-turn, go cruising, take all of those different conditions, and we put them through these narrowband filters. And we do what's called cycle counting. And there's some rainfall methods that we can use to calculate the peak to valley. And these are going to be um, your stress amplitudes, right? And then you compare it against the material properties or SN curves or strain life curves. Minor damage accumulation is something that a lot of people do. So we categorize each frequency and what kind of damage we get, and then we accumulate all the damage. There are some Q factors and different constants that we use. So what is great about fatigue damage spectrum is basically it puts them in their appropriate frequency bins, and we know exactly how many cycles to failure. And then you can use that as an allowable to see like, yeah, this curve needs to run 64 hours for validation. Okay, so that is a very common method today used. Um, then we talk about sign-on random. Why is sign-on random important? Sign-on random is important because the sign becomes very dominant, right? So they have to be superimposed on the random background. So an engine, for example, will have a lot of sinusoidal tones, or something like a compressor or a propeller. They all have sine tones. So that is why we want to put the sine in the random background, and that is very important. It's called a mixed mode test. On the right hand side, you will see a dominant sign in the background of random. You see how dominant that sign is. So we need to simulate the dominant sign in the background of random. That's why we call it sign on random. There are many techniques for sign. Sign resonance, track and dwell is one of the common things. So basically the machine will track the resonance and then it will dwell on the resonance. The important thing about random versus here, random, we put all the frequencies at the same time. Sign, all the energy is going to be in one concentrated frequency. And that is very different than what a random is. So we have to put both of them in there. So for rotating machinery, repeated, predictable kind of frequencies, we take real data and we do the sign tracking. And we do a lot of these user histories to create run-ups of motors, coast down of motors, and we add it to the field data here over FDS technique for random, and we add those two to create what we call a sign-on random method. It's very common in the industry to add sign and random together and run. The last one I'm going to talk about is SRS or shocks. Why do we run SRS shocks? Unidirectional shocks that we do in real world uh, happen, but they don't really replicate many of the transients that happen in the real world. In the real world, there's a lot of high frequency contents that happen unidirectional, normally goes to low frequency. There's a lot of long duration things, shocks that we see in reality. There's multi-directional, effects that we see in marine environments. So that is why it's really important to do these kind of shocks in addition. And what SRS is basically each frequency, it takes the max acceleration peaks of pulses and does something very similar to what we're doing in sine and random. We do it for shock. And here, the highest acceleration peaks for each frequency is summed up and ran that way. So you have a different amplitude different frequency, you have an equivalent shock response spectra. There are many things in the industry. There are burst random, wave-syn. These are different kinds of um, styles of shock that happen, but these are standard things that developed by researchers. But in reality, they happen sometimes, not all the time. So we synthesize them based on these. We use the synthesis method for this. For example, there's a short duration, high frequency shocks. Then we have some burst random, long duration stationary shocks. So we synthesize them and we get something. And even that is not necessary. You have to go and do a lot of field tests and get the energy correctly so that we don't over test it. Bus pick and rattle test is the last one that I kept in here. A lot of people don't like to hear any buzzing or squeaking or rattling. So we can do this test on the shaker as well. And then we do some movements, and then we put microphones to hear where the buzzing and squeaking and rattling comes from. In the analysis, you can also look at which frequency is making the noise. That is pretty much what I had.